Hello there and welcome to the Sleepy Science channel. I'm so glad you found your way here tonight. Maybe you've had one of those long days where your mind just won't settle, or perhaps you're the kind of person who finds comfort in the vastness of space rather than the confines of your own thoughts. Either way, you're exactly where you need to be. Tonight, we're going on a journey together, drifting through the solar system and beyond, exploring the quiet majesty of planets spinning in the cosmic dark. There's something deeply soothing about planets, isn't there? They've been circling their stars for billions of years, patient and unhurried, governed by forces so ancient and reliable that they make our daily worries seem beautifully small. Out there in the velvet darkness, worlds of ice and storm and stone are turning slowly, each one a testament to the universe's capacity for wonder. And tonight, you get to learn about them from the comfort of your bed with nothing required of you except to listen, to breathe, and to let yourself drift wherever these words take you. Before we begin our journey, if you're enjoying this content and you'd like to support the channel, consider giving this video a gentle like or subscribing for more bedtime science. But there's no pressure at all. You're here now, and that's what matters. Let your shoulders drop. Let your jaw relax. Feel the weight of your body sinking into whatever surface is holding you. There's nowhere else you need to be. Nothing else you need to do. Just you and me and the planets waiting patiently in the dark. We'll be exploring facts about these distant worlds, from the familiar ones in our own solar system to the strange and beautiful exoplanets orbiting stars we can barely see. We'll talk about storms that have raged for centuries, about moons that might harbor hidden oceans, about atmospheres made of things you've never imagined. Each fact is a small window into the vast cosmic story, and you don't need to remember any of it. Just let the words wash over you like waves, gentle and rhythmic, carrying you closer and closer to sleep. So settle in. Adjust your pillow one last time. Close your eyes if you haven't already, or let them grow soft and heavy if you're still watching. Take a slow, deep breath in through your nose and let it out through your mouth like a sigh. Perfect. You're doing wonderfully. Now let's begin our gentle drift through the planets, those ancient travelers of space, spinning their slow and eternal dance in the darkness between stars. Our journey begins with Mercury, the smallest planet in our solar system and the closest to the Sun, a tiny world of extremes that somehow manages to be both furnace and freezer at the same time. During its long days, which last 58 Earth days, the surface temperature can soar to a scorching 430 degrees Celsius, hot enough to melt lead. But without a substantial atmosphere to trap that heat, the night side plunges to minus 180 degrees Celsius, creating one of the most dramatic temperature swings anywhere in the solar system. Imagine standing on that boundary line between Mercury's day and night, 1 foot in searing heat and 1 in bitter cold, watching the sun hang enormous in the black sky. It's a reminder that planets don't need to be comfortable to be fascinating, that beauty exists even in these hostile extremes. Venus, our neighboring world, spins so slowly on its axis that a single day there lasts longer than its year. It takes Venus about 243 Earth days to complete one rotation, but only 225 Earth days to orbit the Sun, creating a strange temporal paradox where the planet completes its journey around our star before it finishes a single turn. If you could stand on Venus's surface beneath its crushing atmosphere and thick sulfuric acid clouds, you would experience a day that stretched on almost endlessly, the sun barely crawling across the sky. Time moves differently there, patient and unhurried, as if Venus decided long ago that there was no reason to rush through existence. In the vastness of space, even something as fundamental as day and night becomes flexible, malleable, a reminder that the universe contains rhythms we've never imagined. Mars, that rusty red wanderer, experiences seasons just like Earth does, but they last almost twice as long because a Martian year spans 687 Earth days. The planet tilts on its axis at roughly the same angle as Earth, about 25 degrees, which means that as it orbits the Sun, different hemispheres receive varying amounts of light, creating spring, summer, autumn, and winter. But imagine a winter that stretches for months beyond what you're used to, or a spring that takes its time unfurling across dusty plains and ancient impact craters. There's something peaceful about that extended rhythm, seasons that don't hurry, that give the planet time to breathe and change gradually. When spacecraft have photographed Mars throughout its long year, they've captured the advance and retreat of polar ice caps, watched frost form and vanish on the Martian soil, witnessed the slow, patient dance of a world experiencing time at its own pace. Jupiter, the giant of our solar system, hosts a storm so large that 3 Earths could fit inside it side by side. The Great Red Spot has been raging for at least 350 years, possibly much longer, a swirling anticyclonic tempest in Jupiter's southern hemisphere with wind speeds exceeding 400 kilometers per hour. But here's what's remarkable. This storm, despite its violence, has been slowly shrinking. Observations from the 1800s show it was much larger then, and it continues to decrease in size even now, though it remains immense by any earthly standard. There's something almost soothing about a storm that's been raging since before your great-great-great-great-grandparents were born, something that makes our own troubles feel temporary and small. That storm has outlasted empires, witnessed the entirety of the modern age, and continues its slow rotation in Jupiter's atmosphere, a testament to persistence and the strange kind of stability that can exist even in chaos. Saturn's moon Titan is the only moon in our solar system with a substantial atmosphere, thicker even than Earth's, composed mainly of nitrogen with clouds of methane that rain down onto the surface. But because Titan is so cold, averaging minus 179 degrees Celsius, that methane exists as a liquid, forming rivers and lakes and seas across the moon's frozen landscape. Imagine standing on Titan's shore beside a lake of liquid methane, watching waves lap gently at the hydrocarbon sand, while overhead the thick orange atmosphere diffuses Saturn's distant sunlight into a perpetual twilight. It's a place where the familiar processes of Earth, erosion and weather and hydrologic cycles, play out in entirely alien materials. Rivers carved into frozen water ice carry liquid methane toward methane seas, creating a landscape that would feel recognizable and completely strange all at once. A reminder that nature's patterns repeat across the cosmos in endlessly creative variations. Neptune, that distant blue giant, experiences the strongest winds in the solar system, with gusts reaching 2,000 kilometers per hour, faster than the speed of sound on Earth. These incredible winds whip around the planet in the opposite direction of its rotation, creating jet streams and storm systems in Neptune's cold atmosphere of hydrogen, helium, and methane. The methane gives Neptune its striking blue color, absorbing red light and reflecting blue back into space, making it look like a serene marble hanging in the outer darkness. Despite being so far from the Sun, receiving 900 times less sunlight than Earth, Neptune somehow generates these ferocious winds through internal heat, energy left over from the planet's formation still radiating outward after 4.5 billion years. There's something profound about that. A world so distant and cold still carrying the warmth of its birth, still dynamic and alive in its own way. Winds screaming through an atmosphere while the planet glides silently through the dark. The Earth, our home, is the only planet in the universe we know for certain harbors life, but it's also doing something remarkable that we rarely think about. It's constantly singing. Our planet generates a low-frequency hum, a continuous vibration detected by seismometers, caused by ocean waves, atmospheric pressure changes, and the movement of magma deep beneath the crust. This hum exists at frequencies too low for human ears to hear, but it's always there, a gentle reminder that the Earth itself is alive in ways we don't fully understand. As you lie here now, the ground beneath your building, beneath the soil and rock, is humming its ancient song, has been humming it since long before humans existed and will continue long after we're gone. You're resting on a planet that vibrates with quiet music, and somehow that makes the world feel a little less solid, a little more mysterious, a gentle living thing carrying you through space. Uranus spins on its side, tilted at an angle of 98 degrees, meaning its poles experience 42 years of continuous sunlight followed by 42 years of complete darkness. Scientists believe this extreme tilt resulted from a massive collision with an Earth-sized object billions of years ago, a cosmic impact that knocked the planet over and left it rolling around the Sun like a barrel. Imagine living on Uranus if such a thing were possible, experiencing a summer that lasted your entire childhood and young adult life, the Sun circling endlessly around the horizon, never setting, and then a winter of equal length, decades of unbroken night. The seasons there don't mark a year, they mark generations. There's something strangely peaceful about that thought. The idea that change can happen on timescales so vast they're almost permanent, that a season can outlast a human lifetime, can feel eternal even though it's just another phase in the slow, patient turning of a world. Venus's atmosphere is so dense that the pressure at the surface is equivalent to being 900 meters underwater on Earth, 90 times the pressure we experience at sea level. If you could somehow stand there, you would be crushed, but before that, you would notice something strange. The air would be so thick it would act almost like a liquid, distorting light and slowing movement. Dropping an object wouldn't make it fall quickly. It would drift downward slowly through the dense atmosphere, almost floating. The entire environment would feel heavy and viscous, less like standing on a planet and more like existing at the bottom of an ocean of air. Even sound would travel differently there, faster and richer through the dense medium, meaning the wind howling through Venus's landscape would sound deeper, more resonant. It's a world where the boundary between air and liquid blurs, where atmosphere becomes something you could almost swim through, strange and alien, but governed by the same physics that govern the breeze touching your face on a summer afternoon. Mars's Olympus Mons is the tallest volcano in the solar system, rising 25 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. But because Mars has a much weaker gravitational pull than Earth, and because Olympus Mons grew over billions of years through countless gentle eruptions, its slopes are remarkably gradual, averaging only 5 degrees. If you started climbing this mountain, you might not even realize you were ascending. The slope would be so gentle you could walk up it without difficulty, and the horizon would always look flat because of the mountain's enormous base, 600 kilometers wide. You could hike for days, watching the Martian landscape slowly fall away beneath you, the atmosphere growing even thinner than it already is, and never encounter a steep cliff or difficult scramble. Eventually, you would stand at the summit, higher than any human has ever stood on any world, and look out across a view that stretched hundreds of kilometers in every direction, the curve of Mars visible at the edges, the sky above you transitioning from pink to almost black because you'd be standing above much of the atmosphere itself. Jupiter's moon Europa is covered in a thick shell of water ice that's fractured and refrozen into complex patterns. And beneath that ice lies an ocean that may contain twice as much water as all of Earth's oceans combined. The ice cracks and shifts, creating ridges and chaos terrain, because Europa is constantly squeezed and stretched by Jupiter's immense gravitational pull as the moon orbits, generating tidal heating that keeps the subsurface ocean liquid despite being so far from the sun. Scientists believe this hidden ocean could be one of the best places in our solar system to search for extraterrestrial life. A dark water world sealed beneath kilometers of ice, where hydrothermal vents on the ocean floor might provide energy and chemistry similar to the vents in Earth's oceans where life may have originated. Imagine that ocean, vast and dark and silent, currents flowing in eternal night, perhaps home to organisms that have never seen sunlight, have never even conceived of such a thing. Europa reminds us that life, if it exists elsewhere, might thrive in places that seem inhospitable to us, might find beauty in darkness, might call a hidden ocean home. Saturn's rings, those beautiful bands of ice and rock that circle the planet's equator, are surprisingly thin considering their vast diameter. The rings span hundreds of thousands of kilometers across, wide enough that you could fit dozens of Earths side by side within their reach, yet they're only about 10 meters thick in most places, sometimes even thinner. If you could shrink Saturn and its rings down proportionally, the rings would be thinner than a sheet of paper relative to their width, a vast disk of orbiting particles spread out in a layer so delicate it seems impossible. Despite their fragility, they've likely existed for hundreds of millions of years, possibly since the solar system's formation. Countless trillions of ice crystals and rocky fragments orbiting together in gravitational harmony. Each particle is its own tiny moon, following Kepler's laws, caught in a dance that creates one of the most beautiful sights in the solar system. From Earth, even through a small telescope, you can see these rings, this structure so thin and so vast, and feel connected to something ancient and gracefully balanced. Mercury has almost no atmosphere to speak of, just a thin exosphere of atoms blasted off its surface by solar wind. And this means the sky there would always be black, even during the day when the sun blazes enormous and bright overhead. Without air molecules to scatter sunlight, there would be no blue sky, no gradual twilight, just the stark contrast of brilliant sunlight on the surface and the deep black of space above. Stars would be visible even at noon if you looked away from the sun, constant companions in the darkness, and Earth would shine as a bright bluish point of light, sometimes visible as a morning or evening star just as Venus appears to us. There's something profound about a place where day doesn't make the stars disappear, where the boundary between day and night exists only as a line on the ground, rather than a transformation of the sky itself. Mercury reminds us that the soft blue dome we see above Earth is a gift of our atmosphere, a gentle filter between us and the cosmos, and that most places in the universe exist under skies of permanent night regardless of whether their sun is up or down. Venus rotates in the opposite direction from most planets, a retrograde motion that means the sun rises in the west and sets in the east. If you could survive on Venus's surface, which you couldn't because of the crushing pressure and searing heat, you would see the sun move backwards across the sky compared to its motion on Earth, crawling slowly from the western horizon toward the eastern over the course of that incredibly long Venusian day. Scientists aren't entirely sure why Venus spins backward. Perhaps another massive collision in the distant past knocked it into this reverse rotation, or perhaps gravitational interactions with the sun and its thick atmosphere gradually slowed and reversed its spin over billions of years. Either way, Venus decided to do things differently, to turn against the general flow of the solar system, and there's something almost defiant and beautiful about that. The planet follows its own rhythm, unbothered by convention, a reminder that even in a system governed by gravity and orbital mechanics, there's room for the unexpected, for worlds that march to their own strange and solitary drummers. Mars has two small, irregularly shaped moons named Phobos and Deimos, both probably captured asteroids rather than moons that formed alongside the planet. Phobos, the larger one, orbits so close to Mars that it completes 3 orbits in a single Martian day, rising in the west and setting in the east because it's moving faster than Mars rotates. Over millions of years, Phobos is gradually spiraling inward, getting closer to Mars, and eventually, in perhaps 50 million years, it will either crash into the planet or break apart from tidal forces, creating a temporary ring system around Mars. There's something bittersweet about that. A moon that's been orbiting faithfully for billions of years now slowly falling toward its destruction. But also something beautiful about the ring system that might result. Ice and rock spreading out around Mars in delicate bands that would shimmer in the sunlight. Nothing in the universe is permanent. Even the relationships between planets and moons evolve and end, but they leave beauty in their passing, transformations that continue the cosmic story in new directions. Jupiter generates more heat than it receives from the sun, radiating about 1.6 times as much energy into space as it absorbs, leftover warmth from the planet's formation still slowly leaking out after 4.5 billion years. When Jupiter coalesced from the solar nebula, gravitational compression generated tremendous heat, and the planet is still cooling down, contracting ever so slightly, releasing that ancient warmth into the cold of space. This internal heat drives Jupiter's violent weather, powers those incredible winds and storms, creates rising and sinking currents in the planet's thick atmosphere of hydrogen and helium. In a sense, Jupiter is still glowing with the memory of its birth, still carrying that initial spark of creation, and will continue radiating this heat for billions of years more. It's a reminder that planetary formation released energies so vast that their echoes persist across eons, that worlds can carry the warmth of their creation like a torch passed across unimaginable spans of time, still burning however faintly, still part of the original fire that lit when the solar system was new. Titan's atmosphere creates an anti-greenhouse effect, where the thick haze actually blocks more sunlight than the greenhouse gases trap, making the surface colder than it would be otherwise. The organic haze, created when sunlight breaks apart methane molecules and they recombine into complex hydrocarbons, shrouds the moon in an orange blanket that reflects and scatters light before it can reach the ground. Ironically, this same haze that cools Titan today might be similar to the hazes that existed on early Earth, and studying Titan gives scientists insights into what our own planet might have looked like billions of years ago before life transformed our atmosphere. There's something poetic about studying the past by looking at distant moons, about finding Earth's ancient analogue spinning around Saturn, half familiar and half alien. Titan is like a message in a bottle from our own history, a place where chemistry similar to early Earth's plays out on a frozen stage, and every observation brings us closer to understanding not just Titan but ourselves, where we came from, how we got here. Neptune's moon Triton orbits in the opposite direction from Neptune's rotation, a retrograde orbit that proves Triton wasn't born alongside Neptune, but was captured from the Kuiper belt, probably a dwarf planet similar to Pluto, before it wandered too close to Neptune's gravitational influence. Triton is geologically active despite being one of the coldest objects in the solar system, with nitrogen geysers that erupt through its icy crust, shooting dark material kilometers high, before it drifts down to create dark streaks across the moon's frozen plains. This activity is powered not by internal heat, but by seasonal heating from the distant sun, weak sunlight penetrating the ice and warming trapped nitrogen, until pressure builds enough to break through. It's remarkable that even so far from the sun, even in temperatures approaching absolute zero, there's still enough energy for activity, for change, for geysers erupting on a captured moon circling backward around its adopted planet. Triton reminds us that the solar system remains dynamic even at its frozen edges, that dormancy and death aren't the same thing, that worlds continue their quiet transformations in the outer darkness. You're doing wonderfully. Just let yourself breathe slowly, in through your nose and out through your mouth, releasing any tension you might be holding. These planets we're exploring have been spinning through space for billions of years, patient and unhurried, and their stories will still be there tomorrow. Right now, all you need to do is listen, or drift, or simply exist here in this moment. There's no test, nothing to remember. Let the words wash over you like gentle waves, carrying you deeper into relaxation, deeper into that soft space between waking and dreaming. You're exactly where you're meant to be. Earth's magnetic field acts like an invisible shield, protecting us from the constant stream of charged particles flowing from the sun called the solar wind. Without this magnetosphere, the solar wind would gradually strip away our atmosphere, leaving Earth barren and cold like Mars, which lost most of its magnetic field billions of years ago. The magnetic field is generated by the motion of molten iron in Earth's outer core, a dynamo effect where convection currents and the planet's rotation create electric currents that produce magnetism. This field extends thousands of kilometers into space, deflecting solar particles toward the poles where they interact with atmospheric gases to create auroras, those beautiful shimmering curtains of green and red light in Arctic and Antarctic skies. As you sleep tonight, that magnetic field surrounds you, has surrounded every human who has ever lived, an invisible embrace holding our atmosphere close, making life possible. The planets teach us that the systems sustaining us are often invisible, operating quietly in the background, faithful and constant. Uranus appears as a featureless blue-green disk in most photographs because its methane atmosphere absorbs red light, but beneath that calm exterior lies a bizarre internal structure unlike any other planet. Uranus, along with Neptune, is often called an ice giant rather than a gas giant because, while it has hydrogen and helium in its atmosphere, most of its mass consists of ices, water, methane, and ammonia compressed under extreme pressure into hot, dense fluids. Scientists believe Uranus doesn't have a defined surface. Instead, the atmosphere gradually transitions into this hot ice mantle, which surrounds a small rocky core. Recent research suggests that within this mantle, pressure and temperature conditions might cause carbon to crystallize out as diamonds that rain slowly downward toward the core, creating diamond rain storms in Uranus's deep interior. It's one of the strangest weather phenomena imaginable, gemstones falling through compressed fluids on a planet rolling sideways through the outer solar system. A reminder that nature's creativity extends to places we'll never visit, processes we can barely imagine. Venus's thick clouds of sulfuric acid droplets completely hide the surface from view, but radar mapping from spacecraft has revealed landscapes just as diverse as Earth's, with vast volcanic plains, highland regions, and impact craters. One intriguing feature is the tessera terrain, regions of highly deformed crust that look like crumpled paper, created by intense compression and folding of Venus's surface. These tesserae are some of the oldest terrains on Venus, highlands that rise above the volcanic plains like islands, possibly remnants of ancient continents from a time when Venus might have been more hospitable. There's an ongoing debate about whether Venus ever had oceans. Some scientists believe the planet might have been Earth-like for billions of years before a runaway greenhouse effect transformed it into the hostile world it is today. If that's true, Venus represents a cautionary tale, a world that once might have been our twin before its atmosphere turned against it. But even in its current state, shrouded and inhospitable, Venus continues to fascinate us, continues to hide secrets beneath its clouds. Mars's atmosphere, thin as it is, occasionally produces clouds, fog, and even snowfall, particularly at the planet's poles. The snow that falls on Mars isn't water ice like Earth's snow but carbon dioxide ice, dry ice, forming when temperatures in the Martian atmosphere drop low enough for CO2 to crystallize directly from gas to solid. This happens mostly at night during winter, and while the snowflakes sublimate before reaching the ground in most regions, at the poles they contribute to seasonal ice caps that advance and retreat throughout the Martian year. Imagine snow falling on Mars's cold deserts, dry ice crystals drifting down through the thin pink sky to settle on ancient rocks and rust-colored sand. There's weather happening on that distant world even now as you rest here, clouds forming and dissipating, frost appearing at dawn and vanishing by noon, the planet experiencing its own rhythms of atmosphere and temperature, seasons and cycles that continue whether anyone is there to observe them or not. Jupiter's moon Ganymede is the largest moon in the entire solar system, bigger than the planet Mercury, and it's the only moon known to have its own magnetic field generated by internal processes rather than induced by a nearby planet. This magnetosphere is relatively weak, only about 1% the strength of Earth's, but it creates auroras at Ganymede's poles just like Earth's auroras, shimmering lights where Ganymede's magnetic field interacts with Jupiter's powerful magnetosphere. The fact that Ganymede generates its own field suggests it has a liquid iron core that's still convecting, which in turn implies internal heat, which raises interesting questions about what might exist beneath the moon's icy surface. Like Europa, Ganymede probably harbors a subsurface ocean, a salty sea sandwiched between layers of ice, insulated from the cold of space by kilometers of frozen water above. Every large icy moon we study seems to hide an ocean inside, suggesting that liquid water, one of life's requirements, might be far more common in the universe than we once thought. Saturn's hexagon-shaped jet stream around its north pole has puzzled scientists since its discovery. This six-sided pattern, nearly 30,000 kilometers across, bigger than two Earths side by side, has been stable for decades at least, rotating every 10 hours as Saturn spins. The hexagon is a standing wave pattern in the jet stream, created by the interaction of winds moving at different speeds, but why it forms a hexagon rather than some other shape remains mysterious. Similar patterns can be created in laboratory experiments with rotating fluids, but seeing one occur naturally on such an enormous scale is breathtaking. Each side of the hexagon is longer than Earth's diameter, and at its center sits a massive hurricane-like storm with an eye 50 times larger than hurricane eyes on Earth. There's something almost artificial-looking about it, as if someone drew the hexagon on Saturn's atmosphere with a cosmic compass, but it's entirely natural, a geometric pattern emerging from chaos, order appearing spontaneously from the turbulent flow of clouds and wind. Mercury's core is enormous relative to the planet's size, making up roughly 61% of Mercury's volume compared to only 17% for Earth. This oversized core, composed mainly of iron and nickel, means Mercury is the second densest planet in the solar system after Earth, denser even than Venus despite Venus being much larger. Scientists believe Mercury might have formed with more rocky mantle material, but a massive collision in the early solar system blasted away much of that outer layer, leaving the planet with a proportionally huge core. This collision theory explains not only the core's size, but also Mercury's unusual density and composition. The planet, in a sense, is mostly metal, a dense ball of iron wrapped in a relatively thin shell of rock, and this structure makes it distinctly different from any other terrestrial planet. Mercury's violent past shaped its present, and now it orbits the Sun as a small, dense reminder that planetary formation was a chaotic process, full of impacts and transformations that left each world uniquely scarred and structured. Venus's day is longer than its year, but there's another temporal strangeness. The planet takes 225 Earth days to orbit the Sun, but because it rotates backward so slowly, the time from one sunrise to the next sunrise, what we'd call a solar day, is only 117 Earth days. This means that despite Venus's incredibly slow rotation, the Sun actually appears to move across the sky at a reasonable pace once you account for the planet's orbital motion. If you were standing on Venus, you'd experience about 2 sunrises per Venusian year, these incredibly rare events when the Sun finally crawls up from the eastern horizon after months of darkness. Time on Venus operates according to rules that feel intuitive and bizarre simultaneously, a place where you have to think carefully about what words like day and year actually mean. It's a reminder that our earthly assumptions about time don't apply universally, that other worlds experience duration and cycles in ways that challenge our intuition, that the universe is under no obligation to organize itself according to human comprehension. Mars experiences dust storms that can occasionally grow to encompass the entire planet, shrouding the surface in a rusty haze that can last for weeks or even months. These global dust storms occur roughly every 3 to 4 Martian years, triggered by seasonal temperature differences and the resulting winds that lift fine dust particles into the thin atmosphere. Once airborne, the dust absorbs sunlight and heats the surrounding air, creating even stronger winds that lift even more dust, a positive feedback loop that can escalate a regional storm into a planet-wide event. During these storms, the Sun becomes dim and reddish as seen from the surface. Temperatures moderate because the dust blanket traps some heat at night and blocks sunlight during the day, and solar-powered rovers like Opportunity can find themselves starved of energy, waiting patiently in the gloom for the skies to clear. There's something dramatic about a storm that swallows an entire world, yet also something peaceful about the patience required, the waiting, the certainty that eventually the dust will settle and the sun will shine clearly again. Jupiter's magnetosphere is the largest structure in the solar system, extending millions of kilometers into space, far enough that if you could see it from Earth, it would appear several times larger than the full moon in our sky. This enormous magnetic bubble is generated by electric currents in Jupiter's metallic hydrogen layer, pressurized hydrogen that acts like a liquid metal due to the immense pressures deep in the planet's interior. The magnetosphere traps charged particles, creating intense radiation belts that would be lethal to unshielded astronauts and can damage spacecraft electronics. Jupiter's moon Io, the most volcanically active body in the solar system, constantly spews sulfur and oxygen into space from its numerous volcanoes, and much of this material becomes ionized and trapped in Jupiter's magnetosphere, creating a donut-shaped cloud of plasma called the Io plasma torus. This makes Jupiter not just a planet but an entire complex electromagnetic system, a generator and particle accelerator on a planetary scale, creating phenomena that blur the line between planetary science and astrophysics. Titan's lakes and seas of liquid methane show evidence of wind-driven waves, shorelines that change over time, and evaporation cycles similar to Earth's water cycle, except everything happens with methane instead of water. The Cassini spacecraft detected a glint of sunlight reflecting off one of Titan's northern lakes, proof that the surface was liquid and relatively calm at that moment, acting like a mirror billions of kilometers away. Some of Titan's lakes appear to be fed by methane rain and by rivers draining the surrounding highlands, while others might be fed by underground aquifers of liquid methane seeping up through the icy bedrock. The shorelines show evidence of erosion, coves and bays, familiar coastal geography created by alien substances. Scientists have even detected seasonal changes in these lakes, suggesting that Titan has a hydrological cycle with all the complexity of Earth's, with evaporation, cloud formation, precipitation, and runoff, all playing out in temperatures cold enough to freeze any Earth organism solid instantly. It's a parallel world, running similar processes with different materials, a reminder that Earth's patterns might be templates that nature reuses throughout the universe. Neptune's vivid blue color, deeper and richer than Uranus's pale cyan, comes from methane in its atmosphere, but Neptune appears bluer than it should based on methane concentration alone, suggesting there's another component, possibly an unknown chemical, contributing to its striking color. The planet's appearance has puzzled scientists because Uranus and Neptune have similar atmospheric compositions, yet Neptune's color is distinctly more saturated. Whatever the cause, that deep azure makes Neptune one of the most visually striking objects in the solar system, a sapphire suspended in the darkness at the edge of the planetary system. Neptune was the first planet discovered through mathematical prediction rather than direct observation. Astronomers noticed that Uranus's orbit wasn't quite matching predictions, calculated where an unknown planet would need to be to cause those discrepancies, pointed their telescopes at that spot, and found Neptune almost exactly where the math said it would be. It was a triumph of human reasoning, of understanding gravity well enough to deduce the existence of a world we'd never seen, a reminder that the universe follows laws we can comprehend even when it hides its secrets. Earth's atmosphere is relatively thin, about 100 kilometers deep if you measure to where space officially begins. But that thin shell contains all the air that every organism has ever breathed, all the weather that's ever happened, all the clouds and winds and storms. If Earth were shrunk to the size of an apple, the atmosphere would be thinner than the apple's skin, yet it makes all the difference between a living world and a barren rock. The atmosphere creates pressure that allows liquid water to exist, traps heat that moderates temperatures, blocks harmful radiation, and transports moisture and energy around the planet. Without it, Earth would be silent because sound needs air to travel, cold because heat would radiate directly into space, and dead because life as we know it requires atmospheric protection. As you breathe slowly in and out right now, you're participating in the same atmospheric cycles that have sustained life for billions of years, sharing air with everything that breathes, connected through this thin shell of gases to the planet itself. Uranus has 13 known rings, much fainter and darker than Saturn's brilliant bands, made of dust and dark particles rather than ice, probably material from shattered moons or captured debris. These rings weren't discovered until 1977, when Uranus passed in front of a star, and astronomers noticed the starlight dimming and brightening in a pattern that revealed the ring's existence. Because Uranus spins on its side, its rings orbit vertically relative to its orbit, creating a bizarre configuration where the rings sometimes appear face-on from Earth and other times edge-on, depending on where Uranus is in its 84-year orbit around the Sun. The rings are young compared to the planet itself, perhaps only a few 100 million years old, and they're likely temporary, gradually spiraling inward until they fall into the planet's atmosphere or get ejected into space. Everything in planetary systems evolves and changes. Even seemingly stable features are just momentary configurations and processes that play out over millions or billions of years, stable enough to seem permanent from our brief human perspective, but transient on cosmic timescales. Venus rotates so slowly that its atmosphere circles the planet much faster than the surface turns, a phenomenon called superrotation where winds at cloud-top level travel at 300 kilometers per hour, completing a full circuit around Venus in just 4 Earth days. Scientists don't fully understand what maintains this superrotation. It's one of the major unsolved mysteries about Venus's atmosphere. The fast-moving clouds create a Y-shaped pattern in ultraviolet images, an atmospheric wave that stretches from pole to pole, changing shape over days and weeks. Down at the surface, winds are much gentler, only a few kilometers per hour, but the air is so dense that even these slow winds carry tremendous force, pushing against anything in their path. Venus's atmosphere has its own life, its own dynamics independent of the solid planet below, spinning and churning while the surface barely turns. Another example of how worlds can contain multiple systems operating at different speeds, overlapping but following their own rhythms. Mars has a massive canyon system called Valles Marineris that stretches 4,000 kilometers along the planet's equator, 7 kilometers deep, and up to 200 kilometers wide in some places. To put that in perspective, it's roughly 4 times deeper than the Grand Canyon and 10 times longer, so vast that if it were on Earth, it would stretch from Los Angeles to New York. The canyon wasn't carved by flowing water like Earth's canyons. Instead, it formed primarily through tectonic activity, the Martian crust splitting and collapsing billions of years ago, possibly related to the formation of the massive Tharsis volcanic region that bulges from Mars's surface nearby. Standing on one rim of Valles Marineris, you wouldn't be able to see the opposite rim. It would be beyond the horizon, and the canyon would appear as an endless cliff dropping away into shadowed depths. Water did flow through parts of this canyon system later in Mars's history, creating branching channels and tributary valleys, but the main structure is a scar from the planet's interior processes, a wound in the Martian surface that's never healed, preserving ancient history and frozen geology. Jupiter's Great Red Spot is cold at its top, with cloud temperatures around -160 degrees Celsius. But the storm penetrates deep into Jupiter's atmosphere, where temperatures and pressures increase dramatically. The storm is an anticyclone rotating counterclockwise in Jupiter's southern hemisphere, with winds at the edges moving in opposite directions, creating a shear zone that helps confine the storm and keep it coherent. What's remarkable is how stable this storm has been despite being composed of nothing solid, just gas and clouds rotating according to atmospheric dynamics. There's no ground to anchor it, no geographic feature causing it. It persists through its own internal momentum, and the energy flows in Jupiter's atmosphere. Astronomers have watched the Great Red Spot change color, shifting from brick red to pale salmon and back again, possibly due to changes in the chemical composition of the clouds or varying amounts of sunlight reaching different atmospheric layers. The storm is like a living thing, breathing and changing while maintaining its essential identity, a testament to how pattern and structure can emerge and persist even in chaos. Titan's thick atmosphere extends hundreds of kilometers above its surface, about 10 times higher than Earth's atmosphere extends, because Titan's weak gravity, only 14% of Earth's, allows gases to spread out more. This extended atmosphere means that Titan would have amazing sunrises and sunsets if the haze didn't scatter so much light, with the sun's rays traveling through a long path of atmosphere, creating potentially dramatic color gradients. The atmosphere is primarily nitrogen, just like Earth's, which is unusual for a moon, and suggests that Titan might have started with ammonia ices that were broken apart by ultraviolet light or impacts, releasing nitrogen that accumulated over time. The atmospheric pressure at Titan's surface is 1.5 times Earth's sea level pressure, meaning a human could walk on Titan without a pressure suit, needing only warmth and oxygen, making it one of the most hospitable places in the solar system despite being one of the coldest. You could fly on Titan with simple wings attached to your arms. The thick atmosphere and weak gravity would make human-powered flight easy, letting you soar over those methane lakes and hydrocarbon dunes like a bird in a dream. Take a moment to notice your breathing. You don't need to change it, just observe how natural and automatic it is, how your body knows exactly what to do. These planets we're exploring don't breathe, but they have their own rhythms, their own cycles of day and night, summer and winter, storm and calm. You're connected to those same cosmic patterns, spinning on a planet that's spinning around a star, part of the vast dance of gravity and motion. Let that thought make you feel small in the best way, held by forces larger than worry or stress, part of something ancient and ongoing. You're safe here. Just keep listening or don't. Either way, you're doing perfectly. Neptune's largest moon, Triton, has a thin atmosphere composed mostly of nitrogen with traces of methane, creating a tenuous envelope around the frozen moon. This atmosphere is incredibly thin, about 14 microbars of pressure compared to Earth's 1,014 millibar sea level pressure, but it's substantial enough to support weather, create hazes, and interact with Triton's surface. The Moon's pink and white coloration comes from frozen nitrogen and methane ice mixed with darker organic material, creating a surface that looks almost pastel in color images, surprisingly delicate for such a cold and distant place. Triton orbits Neptune at a distance of only 350,000 kilometers, closer than our Moon orbits Earth, and this proximity means Triton experiences strong tidal forces that heat its interior despite its frigid surface. Like Europa and Enceladus, Triton might have a subsurface ocean kept liquid by tidal heating, another hidden sea in the outer solar system, another place where life's chemistry might find a foothold in the dark. Mercury's surface is covered with impact craters, evidence of billions of years of bombardment. But one of the most interesting features is called the Caloris Basin, a massive impact crater about 1,500 kilometers across, created when an asteroid or comet slammed into Mercury early in the solar system's history. The impact was so powerful that it sent shockwaves through the entire planet, and on the opposite side of Mercury, directly across from Caloris, the surface has strange, disrupted terrain, sometimes called weird terrain, where the shockwaves focused and broke up the crust into a chaotic, jumbled landscape. It's remarkable that a single impact could affect an entire planet, that you could hit one side hard enough to damage the opposite side, demonstrating just how violent the early solar system was. Mercury's heavily cratered surface is a record of that violence, each crater a moment of catastrophic impact frozen in stone, a reminder that planetary formation wasn't a gentle process, but one of tremendous energy and collision, worlds crashing together to build the planets we see today. Venus's surface is geologically young, relatively speaking, appearing to be only about 300 to 500 million years old based on crater counts, which is young compared to surfaces on Mars or Mercury that preserve impact records from billions of years ago. This suggests that Venus underwent a global resurfacing event, where volcanic activity renewed most of the planet's surface, covering up the ancient cratered terrain. Some scientists believe Venus might experience cyclical episodes of intense volcanism followed by long periods of calm, possibly because Venus lacks plate tectonics like Earth's, and heat builds up in the interior until it's released catastrophically. Others think the volcanism might have been more gradual, with lava flows covering the surface over millions of years. Either way, Venus's face is relatively fresh, suggesting the planet remains geologically active, that volcanoes might still erupt under those sulfuric acid clouds, that the planet continues reshaping itself. It's a dynamic world, not a dead one, still processing heat from its formation, still transforming. Mars's soil contains perchlorates, chemical compounds that are strong oxidizers and would make Martian soil toxic to Earth life and challenging for human agriculture if we ever establish bases there. The discovery of perchlorates by the Phoenix lander in 2008 complicated our understanding of Mars's habitability. These chemicals break down organic molecules, and could destroy any evidence of past life in the surface soil. However, perchlorates also have interesting properties. They lower the freezing point of water, meaning salty brines containing perchlorates could remain liquid at temperatures well below 0 degrees Celsius. This raises the possibility of seasonal liquid water flows on Mars, recurring slope-linear dark streaks that appear on crater walls during warm seasons and fade during winter. Whether these streaks represent liquid water remains controversial, but the presence of perchlorates suggests Mars's surface chemistry is more complex and reactive than simple dust and rocks, that the planet holds surprises in its composition, chemicals that challenge and complicate our search for life, but also hint at dynamic processes we're still working to understand. Jupiter's moon Io is the most volcanically active body in the solar system, with hundreds of active volcanoes constantly resurfacing the moon and filling Jupiter's magnetosphere with sulfur and oxygen. Io's volcanism is driven by tidal heating. Jupiter's immense gravity, combined with gravitational tugs from Europa and Ganymede, constantly kneads Io's interior, generating friction and heat. This heat melts rock, and the pressure sends it erupting through the surface in spectacular volcanic plumes that can reach 300 kilometers high, shooting above the surface in graceful arcs before falling back down, some of it escaping Io entirely to form a donut of ionized particles around Jupiter. Io's surface is a painter's palette of yellows, oranges, whites, and blacks, sulfur and sulfur dioxide in various forms, creating a landscape that looks more like a pizza than a moon, constantly renewing itself, never quiet, never still. There's something extreme and beautiful about Io, a world torn apart by gravitational forces beyond its control, expressing that violence through volcanic fury, creating landscapes that disappear and reform within years, an ever-changing canvas in the outer solar system. Saturn's moon Enceladus is only 500 kilometers across, small enough to fit inside the state of Texas. Yet it's one of the most exciting places in the solar system for astrobiology. Enceladus shoots enormous plumes of water vapor and ice particles from fractures near its south pole, geysers that fountain hundreds of kilometers into space, creating a faint ring around Saturn, the E-ring, made of ice particles from these eruptions. The Cassini spacecraft flew through these plumes and detected not just water but organic molecules, salts, and even molecular hydrogen, chemicals that suggest hydrothermal activity on the floor of Enceladus's subsurface ocean. The hydrogen is particularly interesting because on Earth, certain microbes make a living by combining hydrogen with carbon dioxide, a simple chemistry that might work on Enceladus too. This tiny frozen moon, cold enough to make Antarctica look tropical, harbors a warm, salty ocean beneath its icy shell, an ocean in contact with a rocky core where chemistry happens, where energy flows, where just possibly life might exist in some simple form, microbes floating in dark water, sustained by chemical energy from rocky interactions, never seeing the sun but alive nonetheless. Earth's moon is gradually drifting away from us at a rate of about 3.8 centimeters per year, a consequence of tidal interactions between Earth and the moon. As the moon orbits, Its gravity creates tidal bulges in Earth's oceans, and as Earth rotates, these bulges are dragged ahead of the Moon by Earth's rotation. The gravitational pull of these bulges accelerates the Moon slightly in its orbit, causing it to move outward while simultaneously slowing Earth's rotation, making our days gradually longer. Billions of years ago, the Moon was much closer and Earth rotated much faster, with days lasting only 5 or 6 hours. Billions of years from now, the Moon will be farther away, appearing smaller in the sky, and Earth's days will be longer. This slow dance between planet and Moon is imperceptible on human timescales, but profound over geological time. A reminder that even the most stable-seeming celestial relationships are dynamic, evolving according to physical laws that operate patiently across eons. Uranus's moons are named after characters from the works of William Shakespeare and Alexander Pope, a unique naming convention different from the classical mythology used for most other solar system bodies. Miranda, Ariel, Umbriel, Titania, and Oberon are the 5 major moons, discovered between 1787 and 1948, and they're accompanied by dozens of smaller moons with equally literary names: Juliet, Puck, Cordelia, Ophelia, Desdemona, Rosalind, and many others. Miranda is particularly fascinating, with one of the most bizarre and varied surfaces in the solar system, featuring enormous canyons, strange oval-shaped features called coronae, and terrain that looks like it was broken apart and reassembled haphazardly. Scientists theorize that Miranda might have been shattered by an impact and then gravitationally reassembled, or that internal heating caused dramatic tidal resurfacing. But the truth is we don't fully understand this strange little moon circling a planet that spins on its side. There's something fitting about naming these worlds after literary characters, as if acknowledging that these distant places are as rich with story and mystery as any fiction. Venus's volcanic features include massive shield volcanoes, calderas, and vast lava plains, with some volcanoes rivaling or exceeding the size of terrestrial ones like Hawaii's Mauna Loa. Mont Mons, Venus's tallest volcano, rises 8 kilometers above the surrounding plains, and while we don't have definitive proof of current volcanic activity, recent observations have detected changes in surface brightness and atmospheric sulfur dioxide levels that strongly suggest Venus's volcanoes might still be active. If they are, lava would flow slowly across the surface under those crushing atmospheric pressures, glowing red and orange beneath the thick clouds, heat radiating in an environment already hot enough to melt lead. Venus might be the only other terrestrially active volcanic planet in our solar system, besides Earth and Io, a place where fresh lava might be cooling even now, where volcanic gases might be rising through the atmosphere, where the planet's interior continues expressing itself through fire and molten rock. It's a reminder that planets age differently, that some stay geologically alive for billions of years while others cool and quiet, and Venus, despite its hellish conditions, remains in some ways a living, breathing geological entity. Mars has polar ice caps that advance and retreat with the seasons, but these aren't pure water ice like Antarctic ice. The seasonal caps that grow and shrink are carbon dioxide ice, dry ice, that freezes out of the atmosphere during winter and sublimes back into gas during summer. Beneath these seasonal caps are permanent ice caps that do contain significant water ice, particularly at the North Pole, where radar sounding has revealed layers of water ice mixed with dust, forming alternating bands that record climate cycles, the way tree rings record seasonal changes on Earth. These layered deposits tell us that Mars's climate oscillates over time, driven by changes in the planet's axial tilt and orbital eccentricity, swinging between periods when ice accumulates at the poles and periods when it sublimates and deposits elsewhere. Mars has ice ages just like Earth, driven by similar astronomical cycles, and studying those ice layers gives us insights into the planet's climate history stretching back millions of years. It's humbling to think of climate patterns playing out on Mars with no one to witness them. Ice advancing and retreating in cycles older than human civilization. The planet experiencing its own history independent of ours. Jupiter takes almost 12 Earth years to complete one orbit around the Sun, which means that from Jupiter's perspective, Earth zips around the Sun 12 times for every single Jovian year. If you lived on Jupiter, if such a thing were possible, Earth would appear as a bright wandering star that moved through its cycles incredibly quickly, lapping Jupiter again and again in its orbit. This difference in orbital periods is why Jupiter appears to drift slowly through Earth's constellations, taking about a year to move through each zodiac constellation as seen from Earth. Ancient astronomers noticed this steady wandering and named the planet Jupiter after the king of Roman gods, this bright steady light that moved with unhurried dignity across the sky. From our perspective, Jupiter seems eternal and constant, but from Jupiter's perspective, we're the ones living in fast forward, racing around the Sun while Jupiter takes its time, experiencing seasons that last nearly 3 Earth years each, orbiting at a pace that matches its immense size and gravitational influence. Titan's surface features mountains that rise up to 3,000 meters high, mountains made not of rock but of water ice, frozen so cold it's hard as stone. These mountains, combined with Titan's methane lakes and river valleys, create landscapes that look eerily similar to Earth in some ways, with coastlines and drainage networks and highlands and lowlands, but all composed of alien materials at alien temperatures. Some regions of Titan are covered in sand dunes, not sand made of silicon dioxide like Earth's beaches, but hydrocarbons, complex organic molecules blown into dune shapes by Titan's winds. These dunes are enormous, some stretching hundreds of kilometers, marching across Titan's equatorial regions in parallel bands that speak to consistent wind patterns and decades or centuries of particle transport. Titan has geography, erosion, deposition, all the processes that shape terrestrial landscapes, but rendered in ice and liquid methane and organic haze. A parallel Earth at the edge of the solar system, colder than we can imagine but familiar in its variety and complexity. Neptune appears almost featureless in visible light, except for a few white methane cirrus clouds and occasional dark spots, storm systems similar to Jupiter's Great Red Spot, but far less permanent. The most famous was the Great Dark Spot observed by Voyager 2 in 1989, an anticyclonic storm about the size of Earth spinning in Neptune's southern hemisphere. When the Hubble Space Telescope observed Neptune 5 years later, the Great Dark Spot had disappeared, replaced by other spots that came and went, suggesting Neptune's storms are transient compared to Jupiter's long-lived features. This transience makes sense given how little energy Neptune receives from the Sun, over 900 times less than Earth. The energy driving these storms must come primarily from Neptune's interior heat, and perhaps the balance of forces is such that storms can't maintain coherence as long as Jupiter's can. Still, the existence of these powerful storms on such a distant, cold world reminds us that darkness and distance don't mean dormancy, that planets remain dynamic and weather-producing even at the edge of the planetary system where sunlight barely penetrates. Mercury's orbit is elliptical enough that the planet experiences significant variations in the Sun's apparent size and heating throughout its long day. At perihelion, when Mercury is closest to the Sun, it receives about 2¼ times as much solar energy as at aphelion, the most distant point. This variation, combined with Mercury's slow rotation, creates hot spots on the surface, regions that face the Sun at perihelion and experience the most extreme heating. The combination of Mercury's orbital motion and rotation also creates a strange effect. In some locations on Mercury's surface, an observer would see the Sun rise, then reverse course and set again, then rise again and continue across the sky, all because of how Mercury's orbital motion and rotational motion interact at certain longitudes. Time and motion work strangely on Mercury, creating phenomena that seem impossible from our Earth-bound perspective, reminding us that the laws of orbital mechanics produce different effects depending on the specifics of each world's motion. Venus's thick atmosphere is so good at distributing heat that temperatures at the poles are almost identical to temperatures at the equator, and night-side temperatures are nearly the same as day-side temperatures. Despite Venus's slow rotation creating incredibly long days and nights, the superrotating atmosphere transports heat so efficiently that the entire planet maintains a remarkably uniform temperature of about 460 degrees Celsius at the surface. This is hot enough to glow faintly in the visible spectrum, meaning Venus's surface radiates a dull red heat even at night, though you couldn't see it from above because of the clouds. The uniformity of temperature means Venus has no jet streams like Earth's, no strong temperature-driven wind systems. Instead, the atmospheric dynamics are driven by the absorption of sunlight in the clouds and the resulting convection. Venus teaches us that atmospheres can behave in radically different ways depending on their thickness, composition, and rotation rate, that Earth's weather patterns are just one possibility among many, that the universe contains infinite variations on the theme of air and heat and pressure. Mars's two small moons, Phobos and Deimos, are so small and irregularly shaped that they don't have enough gravity to pull themselves into spheres. Phobos is only about 22 kilometers across at its widest, and Deimos is even smaller at 12 kilometers. From the Martian surface, Phobos would appear about half the angular size of our moon as seen from Earth, while Deimos would look like a very bright star, barely resolving as a disk at all. Neither moon is large enough to create a total solar eclipse on Mars. Instead, they cause partial eclipses or transits where a dark, irregular shape crosses the sun's face. Mars rovers have photographed these transits, watching Phobos's shadow drift across the sun in a series of images that have an eerie beauty, a reminder that even on Mars, moons still cross the sun, creating moments of astronomical alignment. These tiny moons are probably captured asteroids, pieces of the early solar system that wandered too close to Mars and were caught by its gravity, finding themselves permanent companions to a planet they didn't originate with. Jupiter's immense gravity acts as a cosmic vacuum cleaner for the inner solar system, deflecting or capturing comets and asteroids that might otherwise reach Earth. The Shoemaker-Levy 9 comet impact in 1994 demonstrated this dramatically when a fragmented comet crashed into Jupiter, creating dark impact scars in the atmosphere larger than Earth that persisted for months. Without Jupiter's gravitational influence, Earth would likely experience far more frequent large impacts, making the development of complex life more difficult or perhaps impossible. In this sense, Jupiter acts as Earth's protector, a massive shield whose gravity shepherds dangerous objects away or captures them, giving Earth a more stable environment. It's humbling to think that our existence might depend in part on Jupiter's presence, that this giant planet floating so far away has been quietly protecting us for billions of years, catching bullets meant for the inner planets, taking hits that might otherwise strike Earth, fulfilling a role we're only beginning to understand and appreciate. Titan's methane cycle is constantly removing methane from the atmosphere as ultraviolet light breaks it down into more complex hydrocarbons that rain onto the surface. Yet the atmosphere continues to contain about 5% methane, suggesting there must be a source replenishing it. Scientists believe Titan has methane reservoirs, possibly cryovolcanoes that erupt methane from the interior, or methane trapped in subsurface ice that's gradually released. Without this replenishment, Titan's atmospheric methane would be depleted in only 10 to 30 million years, a short time geologically. This implies Titan is geologically active in some way, that its interior is still processing materials and releasing them to the surface, that like Earth with its water cycle, Titan has a methane cycle that connects interior, surface, and atmosphere. It's one of the most Earth-like aspects of this distant moon, not the specific chemistry, but the presence of complex planetary cycles involving phase changes, atmospheric processes, and geological activity, all the elements that make a world feel alive and dynamic rather than static and dead. Notice how relaxed your body feels now, how heavy and comfortable. You might have drifted away from the words for a moment, and that's perfectly fine. These facts about planets will continue whether you're listening closely or floating in that peaceful space between thoughts. The universe is patient. The planets have been spinning for billions of years, and they'll keep spinning tonight as you fall asleep. There's something comforting in that continuity. in knowing that forces larger than us continue regardless of our attention. Take another slow breath. Feel yourself sinking deeper into rest. You're safe, you're comfortable, and you're exactly where you belong. Earth is the only known planet where fire can burn, because fire requires oxygen in significant concentrations, something unique to our atmosphere. The oxygen that makes fire possible comes primarily from photosynthesis, meaning that fire is essentially stored sunlight being released rapidly, ancient solar energy that was captured by plants and then liberated all at once through combustion. This makes fire a biological phenomenon in a sense, something that exists because of life, not despite it. On Venus, Mars, and the gas giants, you couldn't light a match if you tried. There's no oxygen to sustain combustion. This unique aspect of Earth often goes unnoticed. We live on the only world we know where things can burn, where chemistry can proceed rapidly through oxidation, where we can cook our food and stay warm with flames. Even that simple campfire represents something cosmically rare, a phenomenon dependent on the specific composition of our atmosphere, which in turn depends on billions of years of photosynthetic life, transforming the air. Uranus's tipped orientation means that its moons and rings all orbit in that same vertical plane relative to the planet's orbit around the Sun, creating a system that's unique in the solar system. At the solstices, when one pole points directly at the Sun, the rings appear face-on from Earth, and we can see their full structure. At the equinoxes, when Uranus's equator is aligned with the Sun, the rings appear edge-on, sometimes becoming temporarily invisible because they're so thin. This happens roughly every 42 years, half of Uranus's 84-year orbit, creating observing opportunities when astronomers can look for moons close to the planet that are usually lost in the glare of the rings. The next ring plane crossing will happen in the 2040s, and astronomers are already planning observations to take advantage of this unique geometry. Uranus reminds us that planets aren't all oriented neatly like a diagram. They're scattered at different angles, each one carrying the evidence of its own unique formation history and collisional past. Venus's surface pressure and temperature create conditions where carbon dioxide doesn't behave quite like a normal gas. At 460 degrees Celsius and 90 atmospheres of pressure, carbon dioxide on Venus is close to what's called a supercritical state, where the distinction between liquid and gas breaks down, and the substance behaves with properties of both. While Venus's atmosphere isn't technically supercritical everywhere, near the surface it acts more like a fluid than a gas, dense and viscous, almost able to dissolve substances like a solvent. This creates strange effects. Sound travels faster, objects experience more drag when moving through the air, and heat transfer happens differently than in normal atmospheric conditions. Venus's environment is so extreme that it pushes chemistry and physics into regimes we rarely encounter on Earth, making the planet a natural laboratory for studying matter under conditions we can barely recreate in our laboratories, a place where familiar substances behave in unfamiliar ways. Mars's gravity is 38% of Earth's, meaning that if you weigh 100 pounds on Earth, you'd weigh only 38 pounds on Mars. This reduced gravity would affect everything about living on Mars. You could jump nearly 3 times as high, carry much heavier loads and fall much more slowly, though the impact would still hurt because your mass hasn't changed, only your weight. Buildings could be taller and thinner, cars could be lighter, and human physiology would adapt over time, with muscles and bones adjusting to the reduced load, though whether those adaptations would be healthy long-term remains uncertain. The reduced gravity is one reason Mars's atmosphere is so thin. The planet's smaller mass and weaker gravity couldn't hold onto atmospheric gases as well as Earth can, especially after Mars lost its magnetic field and solar wind began stripping the atmosphere away. Walking on Mars would feel bouncy and strange, a constant reminder that you're not on Earth anymore, that every step and jump obeys a different mathematical relationship between force and acceleration. Jupiter's moon Callisto is the most heavily cratered object in the solar system, its surface a palimpsest of impacts dating back billions of years, nearly every square kilometer marked by some ancient collision. Unlike the other Galilean moons, Callisto shows no signs of geological activity, no evidence of internal melting or surface renewal. It appears to be a frozen relic that's barely changed since its formation. This makes Callisto valuable scientifically, because its surface preserves a record of the solar system's early bombardment history, a witness to the violence of planetary formation. Despite being about the same size as Mercury, Callisto has no magnetic field and possibly no metallic core, suggesting it never fully differentiated into layers like most planets and large moons did. Instead, it might be a relatively homogeneous mixture of rock and ice throughout, a body that never quite became a full-fledged world, that stayed frozen in an early state while its sibling moons heated up and evolved. Callisto is a time capsule, the most ancient face in the Jupiter system, patient and unchanging. Titan's atmosphere contains complex organic molecules including polycyclic aromatic hydrocarbons, tholins, and other carbon-based compounds that form when methane molecules are broken apart by sunlight and recombine into more complex forms. These organics give Titan's atmosphere its orange color and create a haze that obscures the surface in visible light. But they're also incredibly interesting from an astrobiological perspective. Some of these compounds are precursors to the chemicals necessary for life, and they rain down onto Titan's surface constantly, accumulating over geological time. Titan's surface might be covered in a layer of these organic molecules, a surface enriched in the building blocks of life, even though it's far too cold for life, as we know it to exist there now. Some scientists speculate that if the Sun eventually enters a red giant phase and heats the outer solar system, Titan might warm enough for its chemistry to become biologically active, that billions of years from now, this distant moon might become a haven for life long after Earth has been consumed by the expanding Sun. A poetic thought about distant futures and life's persistence. Neptune was the last planet predicted and discovered before we started finding planets beyond our solar system, completing the classical solar system of 8 planets. Its discovery in 1846 was a triumph of mathematical astronomy, demonstrating that humans could understand gravity well enough to predict where invisible planets must exist. Since then, Astronomers have discovered thousands of exoplanets orbiting other stars, but Neptune remains special as the frontier of our own planetary system, the last major world before space transitions into the Kuiper Belt, with its population of small, icy bodies. Neptune represents the edge of what we think of as the planetary realm, the outermost guardian at the boundary between the worlds of our Sun and the vast spaces beyond. From Neptune, the Sun appears only as a bright star, still the brightest object in the sky but no longer a disk, and Earth would be utterly invisible without a telescope, a pale blue dot lost in the Sun's glare, offering a perspective on our place in the cosmos that's both humbling and beautiful. Mercury's heavily cratered surface includes features called hollows, shallow depressions with bright walls and floors that appear fresh and young despite Mercury's ancient surface. These hollows seem to form through a process called sublimation, where some material in Mercury's crust, possibly volatiles like sulfur, is being heated by the Sun and vaporizing directly from solid to gas, leaving behind these distinctive features. The fact that this process appears ongoing suggests Mercury's surface is still active in subtle ways, still changing despite being billions of years old, still processing materials in response to the intense solar heating. Mercury teaches us that even ancient, heavily cratered worlds can harbor active processes. That dormancy isn't complete cessation, but rather the continuation of slow, subtle changes that accumulate over geological time. The planet's surface is simultaneously very old, preserving impact craters from the solar system's formation, and very young, with these bright hollows forming potentially within the last few million years, maybe even today, under the intense glare of the nearby Sun. Venus rotates so slowly that the Coriolis effect, which on Earth causes winds and ocean currents to curve and creates rotating storm systems, is almost non-existent at Venus's surface. This is one reason Venus doesn't have hurricanes or cyclones like Earth does. The slow rotation doesn't generate the necessary rotational deflection. Instead, Venus's weather is dominated by convection and the superrotation of the atmosphere, creating weather patterns that look fundamentally different from Earth's. At cloud level, the fast winds do create some Coriolis effects, contributing to wave patterns and atmospheric dynamics, but near the surface where the atmosphere is densest and slowest moving, weather behaves more like simple convection without the spiral patterns we associate with Earth storms. This makes Venus a natural experiment in comparative atmospheric science, showing us what Earth's weather might look like with different rotation rates, helping us understand which aspects of our weather are universal and which are specific to Earth's particular circumstances of size, rotation, and atmospheric composition. Mars's day, called a sol, is only about 40 minutes longer than an Earth day, lasting 24 hours and 39 minutes, which means that daily rhythms on Mars would feel very similar to daily rhythms on Earth. This similarity has been helpful for Mars rover operations. Mission controllers can live on Mars time, shifting their schedules forward by 40 minutes each day to maintain daylight operations on Mars, though this eventually becomes disorienting for humans who aren't naturally suited to a slightly longer day. The near match between Earth and Mars days means that circadian rhythms evolved for Earth might adapt reasonably well to Mars. Unlike the Moon, where days last 29 Earth days, or Venus, where days last months. If humans ever colonize Mars, the day-night cycle would be one of the more familiar and comfortable aspects of the environment, a reminder that despite the cold, thin atmosphere and red dust, Mars shares some fundamental similarities with Earth that make it feel, at least temporarily, like a place we might belong. Jupiter's magnetosphere creates intense auroras at the planet's poles, far more powerful than Earth's northern and southern lights. These Jovian auroras are driven not just by solar wind like Earth's, but primarily by Jupiter's fast rotation and the interaction between the planet's magnetic field and charged particles from Io's volcanoes. The auroras on Jupiter are permanent features, constantly glowing in ultraviolet and visible wavelengths, creating curtains of light that dwarf Earth's most spectacular aurora displays. The energy involved is immense, with Jupiter's auroras generating megawatts of power, enough to power a small city on Earth, all dissipated as light and heat in Jupiter's upper atmosphere. Spacecraft have captured images of these auroras from orbit and flyby, revealing structures that flow and pulse with the 11-hour rotation period of Jupiter's magnetic field. Standing on Jupiter, if you could, you would see the sky near the poles constantly illuminated with shimmering lights, a permanent celestial display, the visible signature of electromagnetic forces on a planetary scale. Titan's thick atmosphere means that its surface receives very little sunlight, less than 1% of what reaches Earth's surface, creating a perpetual twilight even at local noon. This dim lighting combined with the orange haze gives Titan a surreal quality in images captured by the Huygens probe, the only spacecraft that has landed on a moon in the outer solar system. The photographs show a landscape of rounded ice boulders scattered across darker plains, river channels visible in the distance, everything bathed in a dim orange glow that makes the scene look simultaneously familiar and utterly alien. Despite the dimness, there's enough light for photography without a flash, and there would be enough for human eyes to see, though everything would appear in shades of orange and brown because the atmosphere filters out most other wavelengths. Titan is a world of soft light and muted colors, where noon feels like late dusk, where shadows are gentle and indistinct, where you could walk across frozen water ice under a sky that never fully brightens or darkens, caught in eternal twilight. Earth's water, the substance that makes life possible and covers 71% of our planet's surface, is fairly rare in the inner solar system but might be common in the universe overall. Most of Earth's water probably arrived via comets and water-rich asteroids that bombarded the young planet billions of years ago, meaning the water you drink and the oceans covering Earth traveled from the outer reaches of the solar system. Every glass of water contains molecules that have been part of clouds and rivers, drunk by dinosaurs, frozen in glaciers, and split apart by plants for photosynthesis, then recombined millions of times. Water cycles through Earth systems in an endless loop, and the water present now is essentially the same water that existed when Earth formed, neither created nor destroyed, just constantly recycled. This makes water ancient, linking you directly to the early solar system, making every raindrop an ocean wave, a traveler from deep time and deep space, a reminder that the boundary between Earth and the cosmos is more porous than it seems. Uranus's pale blue-green color has become iconic, but recent research suggests it might not always look exactly the same. Observations over the years have shown subtle variations in color and brightness, possibly due to seasonal changes as different hemispheres receive varying amounts of sunlight during Uranus's long year. As spring and summer come to Uranus's northern hemisphere, increased solar heating might cause upwelling in the atmosphere, bringing different materials to visible levels and potentially altering the planet's appearance. These changes unfold slowly, over years and decades from our perspective, but they remind us that planets aren't static images, that they weather seasons and experience atmospheric changes just like Earth does, only at different scales and speeds. Uranus in the 1980s, when Voyager visited, might look subtly different from Uranus today, and both might look different from Uranus 40 years from now when another solstice arrives, demonstrating that even distant planets have variability and change written into their nature. Venus's clouds contain sulfuric acid droplets that form from sulfur dioxide and water vapor combining in the atmosphere, creating one of the most corrosive environments imaginable. These acid clouds are so concentrated that they would destroy most materials, yet they're also where conditions are most Earth-like on Venus. About 50 to 60 kilometers above the surface, in the middle cloud layers, temperatures are around 20 degrees Celsius, room temperature, and while the air is unbreathable and acidic, the pressure is close to Earth sea level pressure. This has led to proposals for floating habitats on Venus, cities suspended by balloons in the more hospitable cloud layers, while the hellish surface remains far below. It's a strange thought. The most Earth-like environment in the entire solar system, outside Earth itself, might be floating in Venus's atmosphere, a thin layer where temperature and pressure align with human comfort even though the chemistry is deadly. Venus reminds us that habitability is multidimensional, that planets can be hostile in some ways while offering surprising opportunities in others, that imagination and engineering might find niches for life in places we initially dismiss as uninhabitable. Mars experiences global dust storms, but between these dramatic events, the planet can be remarkably clear, with blue sunsets that NASA rovers have photographed repeatedly. These blue sunsets occur because Mars's atmosphere, though thin, contains fine dust particles that scatter light differently than Earth's air molecules do. The dust particles are just the right size to scatter red wavelengths more than blue, opposite to what happens on Earth where our thicker atmosphere scatters blue light, making our sky blue and our sunsets red. On Mars, the sky during the day appears butterscotch or salmon-colored because red wavelengths scatter around, but at sunset, when sunlight travels through the most atmosphere, blue wavelengths dominate around the sun, creating an eerie blue glow. It's a beautiful inversion of Earth's sunset, a reminder that even familiar phenomena like the color of sky depend on specific atmospheric conditions. Watching a Martian sunset would be a surreal experience, seeing blue surrounding the sun as it sinks toward the horizon, a touch of earth-colored sky in an otherwise alien world. Jupiter's 4 largest moons, the Galilean satellites discovered by Galileo in 1610, constitute a miniature solar system of their own, each moon distinct and each teaching us something different about planetary science. Io shows us extreme volcanism, Europa hints at subsurface oceans, Ganymede teaches us about magnetic fields in moons, and Callisto preserves ancient surfaces. Together, they demonstrate the range of geological and physical processes possible for moons, and they're all tied locked to Jupiter, always showing the same face toward the planet just as our moon does to Earth. From Jupiter's cloud tops, if you could float there, you would see these moons as bright disks moving across the sky in different directions and at different speeds, eclipsing each other and casting shadows on Jupiter, creating a dynamic celestial ballet. The Galilean moons were the first objects discovered orbiting something other than Earth, proving that not everything circles our planet, providing critical evidence that helped overthrow the geocentric model of the universe. They're historically significant as well as scientifically fascinating, a reminder that small observations can revolutionize our understanding of the cosmos. Titan's subsurface ocean, if it exists as scientists believe, is probably salty, with dissolved minerals and maybe even ammonia acting as antifreeze to keep the water liquid despite the cold. This ocean might be tens to hundreds of kilometers deep, more voluminous than all of Earth's oceans combined, trapped between an icy shell above and possibly a rocky seafloor below, or perhaps separated from the rock by another layer of high-pressure ice. We don't know if Titan's ocean connects to the surface anywhere. There's no evidence of geysers or cryovolcanic activity like on Enceladus or Europa. So if the ocean exists, it might be completely sealed off, a dark water world that's never exchanged material with Titan's surface or atmosphere. Yet if it exists, it represents another potential habitat, another place where chemistry happens in liquid water, where the building blocks of life might interact in ways we don't yet understand. Titan keeps its secrets well, hiding its ocean if it has one beneath ice and obscuring its surface beneath haze, a world that requires patience and persistence to explore but promises profound discoveries. Let your thoughts drift like clouds, slow and aimless. If you're still awake, that's fine. If you've been floating in and out of awareness, that's perfect too. These planets spinning in the darkness don't need you to remember their names or their distances. They exist independent of your attention, patient and eternal, and they'll continue their slow dances through space while you sleep tonight and every night. Feel the weight of your body one more time, sinking into softness. Feel your breath, slow and automatic. You're held by the Earth, the same gravity that keeps the moon in orbit, that keeps us all connected to this spinning rock in space. Rest now. Let go. Neptune's winds, the fastest in the solar system, remain somewhat mysterious because Neptune receives so little energy from the Sun, far less than Jupiter or Saturn, which also have strong winds. The fact that Neptune has such powerful winds despite receiving minimal solar energy suggests the planet must have a very efficient internal heat source and very effective mechanisms for converting that heat into kinetic energy of wind. Some scientists have proposed that Neptune's atmosphere might be especially unstable, or that the temperature difference between the deep hot layers and the cold upper atmosphere creates unusual convection patterns that drive these extreme winds. Whatever the mechanism, Neptune serves as a laboratory for atmospheric physics, showing us that wind speed isn't simply a function of solar heating, that the interplay between internal heat, atmospheric composition, and planetary rotation can produce outcomes we're still working to fully understand. Neptune's winds howl through an atmosphere we've only glimpsed briefly during Voyager 2's flyby, carrying secrets about how planetary atmospheres work in extreme conditions. Mercury's core is gradually cooling and shrinking, and as it does, the planet's surface wrinkles like a dried fruit, creating long, steep cliffs called scarps that can be hundreds of kilometers long and several kilometers high. These scarps formed as Mercury's interior contracted, causing the crust to buckle and fracture, pushing some sections up and over others. The largest scarp, called Discovery Rupes, is about 650 kilometers long, and climbing it would be like scaling a cliff taller than the Grand Canyon is deep, a testament to the forces involved in planetary cooling. Mercury has likely contracted about 7 kilometers in radius since its formation, a small amount relative to the planet's size, but enough to create dramatic surface features. These scarps are found all over Mercury, crisscrossing the surface at different angles, a global network of wrinkles that tells the story of a planet slowly cooling and shrinking over billions of years, its interior radiating away the heat of formation, drawing inward as the metal core solidifies. Venus's atmosphere contains trace amounts of phosphine gas, a discovery announced in 2020 that generated considerable excitement because phosphine on Earth is associated with biological processes or industrial chemistry, not natural geological processes. The detection remains controversial and is being investigated further. But if confirmed and if no geological explanation can be found, it raises tantalizing questions about whether some form of microbial life might exist in Venus's clouds, floating in those habitable layers where temperature and pressure are moderate. Even on a planet as hostile as Venus, life might find a niche, perhaps organisms that spend their entire life cycles airborne, never touching the scorching surface, adapted to acidic clouds and aerial existence. It would be utterly unlike any life on Earth, yet perhaps following similar chemical principles, using the same fundamental building blocks to carve out survival in an environment that seems impossible. Venus might harbor one of the most significant discoveries in history, or the phosphine might have a mundane explanation we haven't thought of yet. But either way, the possibility reminds us to keep questioning and searching. Mars once had a much thicker atmosphere, liquid water on its surface, and possibly conditions suitable for life. But over billions of years, it lost most of that atmosphere to space, transforming from a potentially habitable world to the cold, dry planet we see today. The loss happened gradually as solar wind stripped away atmospheric particles, a process that accelerated after Mars lost its global magnetic field, which had protected the atmosphere from erosion. Evidence for Mars's wetter past is everywhere. Ancient river valleys carved into the surface, sedimentary rocks formed in lakes, minerals that only form in the presence of water, all pointing to a Mars that was warmer and wetter billions of years ago. Whether life emerged during that more hospitable period remains unknown, one of the driving questions behind Mars exploration. Studying Mars helps us understand planetary habitability and how planets can change over time, losing the conditions that made them habitable. A sobering reminder that Earth's habitability isn't guaranteed forever, that planets evolve, and sometimes those evolutions lead to less hospitable conditions. Jupiter's intense radiation environment is one of the major challenges for spacecraft visiting the planet. The radiation belts surrounding Jupiter are so powerful they can damage electronics, degrade solar panels, and would be deadly to unprotected astronauts in minutes. The Juno spacecraft, currently orbiting Jupiter, was designed with extensive shielding and has its sensitive instruments housed in a titanium vault to protect them from radiation. Despite these precautions, Juno's mission is limited by how long its electronics can withstand the radiation bombardment, with the high radiation environment slowly degrading systems over time. The intense radiation comes from Jupiter's powerful magnetic field trapping charged particles, which spiral along field lines and bombard anything in their path with high-energy electrons and ions. This makes Jupiter's moons Io and Europa particularly challenging destinations for future missions. Any lander or rover would need exceptional radiation hardening to survive. Jupiter reminds us that the solar system contains environments as hostile as anything in space. That proximity to a giant planet comes with hazards as well as wonders. Titan is one of only 2 worlds in the solar system besides Earth with stable liquids on its surface, the other being potentially Jupiter's moon Europa beneath its ice shell, though Europa's subsurface ocean doesn't interact directly with space the way Titan's lakes do. This makes Titan unique for studying liquid-based processes beyond Earth, for understanding how lakes and seas behave in different gravity and with different chemistry. The Cassini mission observed waves on Titan's lakes, detected seasonal changes in liquid levels, identified river channels where methane flows, essentially mapping an alien hydrological cycle in operation. Some of Titan's lakes appear to be phantom lakes, depressions where liquid once existed but has since evaporated, leaving behind materials similar to a dry lakebed on Earth. Other lakes are perennial, filled year-round with methane and ethane. Watching Titan's seasons progress through Cassini's 13-year mission gave scientists a time-lapse view of how this alien weather works, how methane moves from atmosphere to surface and back again, creating a climate system that's the most Earth-like in the solar system despite being completely alien in composition. Earth's atmosphere extends much farther into space than most people realize, with the exosphere, the outermost layer, reaching out to about 10,000 kilometers, halfway to the moon. At these altitudes, the atmosphere is so thin that individual molecules can travel hundreds of kilometers without colliding with other molecules, gradually transitioning into the vacuum of space without any clear boundary. Some of Earth's atmospheric atoms escape entirely, lost to space over time, while the solar wind and Earth's magnetic field influence others, creating complex interactions at the boundary between planet and space. This tenuous outer atmosphere demonstrates that planets don't end abruptly. They fade gradually into the space around them, influencing and being influenced by their surroundings, connected to the solar environment in intricate ways. As you lie here breathing air at sea level, remember that the atmosphere extends far above, thinning and cooling, but still part of Earth's envelope, still technically the same ocean of gas that sustains life at the surface. Uranus's magnetic field is tilted nearly 60 degrees from its rotational axis and offset from the planet's center, creating a lopsided, tumbling magnetic field unlike any other planet. As Uranus rotates every 17 hours, this offset tilted field rotates with it, meaning that the magnetic field lines spiral and twist in complex patterns, creating a magnetosphere that wobbles and reconfigures constantly. Scientists don't fully understand why Uranus's field has this strange geometry. It might be generated in a slushy mantle layer rather than a deep metallic core like Earth's field, producing different dynamics. Neptune has a similarly tilted and offset field, suggesting that ice giants might generate magnetism differently than terrestrial planets or gas giants. Flying through Uranus's magnetosphere would be a bizarre experience, with the magnetic field direction changing not just with distance from the planet, but also with the planet's rotation, creating a time-varying magnetic environment that would confuse any compass designed for Earth-like fields. Uranus's magnetosphere is chaotic in a unique way, adding to the planet's list of peculiarities. Venus has been visited by more spacecraft than any other planet except Mars, with numerous Soviet and American probes exploring the planet from orbit and surface throughout the 1960s through 1980s. The Soviet Venera program successfully landed multiple probes on Venus's surface, transmitting images and data from the surface before the harsh conditions destroyed them, usually within an hour or two. These brief moments gave us our only direct views of Venus's surface. Flat rocks scattered across volcanic plains under a dim orange sky. Photographs that look almost familiar until you remember they were taken on another planet under crushing pressure and searing heat. Some Venera probes were equipped with drills and analyzers that determined the composition of Venusian rocks, finding basalt similar to volcanic rocks on Earth, confirming Venus's volcanic nature. The last probe to land on Venus was the Soviet Vega 2 in 1986, and since then, no spacecraft has returned to the surface. Venus stands as a destination explored decades ago and then largely abandoned, with renewed interest only recently as scientists propose new missions to this challenging but scientifically rich world. Mars's largest volcano, Olympus Mons, sits near three other massive volcanoes called the Tharsis Montes, which together form a volcanic region so massive that it creates a noticeable bulge in Mars's shape. This region, the Tharsis Rise, is about 10 kilometers higher than the surrounding terrain and spans 5,000 kilometers across, about a quarter of Mars's circumference. The weight of all this volcanic material has actually affected Mars's rotation over geological time, causing the planet's axis and equator to shift slightly, a process called true polar wander, where a planet's entire outer shell reorients relative to its spin axis. The Tharsis volcanoes likely formed over hundreds of millions of years, as Mars's interior heat found its way to the surface through the same hotspot, building layer upon layer of lava flows without the tectonic plate motion that would move the volcanoes away from the hotspot like happens on Earth with chains like Hawaii. Mars's lack of plate tectonics meant volcanic regions could build up in place, creating singular massive structures instead of chains of smaller volcanoes. Jupiter generates powerful radio emissions that can be detected from Earth, a crackling and whooshing sound when converted to audio, produced by charged particles spiraling along magnetic field lines and electrons, accelerated to high speeds in the magnetosphere. These radio bursts were discovered accidentally in the 1950s, when radio astronomers detected strange signals coming from Jupiter's direction, initially thinking they might be from some terrestrial source of interference. The radio emissions vary with Jupiter's rotation and with the position of Io in its orbit, because material from Io's volcanoes feeds the magnetosphere with charged particles that enhance the radio emissions. Jupiter is literally broadcasting across the solar system, sending out radio waves that travel at the speed of light, reaching Earth about 40 minutes after they're emitted depending on where Jupiter is in its orbit. Amateur radio enthusiasts with the right equipment can detect these emissions, listening to Jupiter's magnetic field at work, hearing the planet in a way that's completely invisible to our eyes. Titan's surface temperature averages minus 179 degrees Celsius, cold enough that ice behaves like rock and methane behaves like water. But Titan's subsurface might be much warmer, possibly even reaching temperatures where liquid water could exist temporarily in pockets or layers. If Titan experiences cryovolcanism, eruptions of water or water-ammonia mixtures from the interior, these would provide windows into the Moon's deep chemistry, places where subsurface materials reach the surface and freeze, creating features different from the surrounding terrain. The Cassini mission found possible evidence of cryovolcanoes, features that look like volcanic calderas or mountains with flows, but definitive proof remains elusive because identifying volcanic features on a world where you can't visit the surface is challenging. If cryovolcanism occurs, it would mean Titan's interior is warm enough for geological activity, that tidal heating from Saturn or decay of radioactive elements keeps the Moon geologically alive beneath its frozen surface, providing energy and chemistry that makes Titan even more interesting as a potentially habitable environment, at least for exotic organisms very different from Earth life. Neptune's largest storm, the Great Dark Spot discovered by Voyager 2, was about the size of Earth and displayed some similarities to Jupiter's Great Red Spot. But unlike Jupiter's long-lived storm, Neptune's dark spot disappeared within a few years. This transience tells us something about the different energetics of these two giant planets. Jupiter's thick atmosphere and strong internal heat, combined with solar heating, create stable conditions for long-lived vortices, while Neptune's weaker energy budget and thinner atmosphere can't maintain these structures indefinitely. However, new dark spots have appeared on Neptune since Voyager's visit, observed by Hubble and ground-based telescopes, suggesting that these storms are a recurring feature, constantly forming and dissipating in Neptune's dynamic atmosphere. Each appearance gives scientists another opportunity to study how storms form and evolve in Neptune's unique environment, building a picture of atmospheric dynamics at the edge of the solar system, where sunlight is weak and internal heat dominates, where weather happens in near darkness at temperatures far below anything on Earth. Mercury's exosphere, that thin veil of atoms around the planet, is constantly being replenished and lost in a dynamic process. Atoms are blasted off the surface by solar wind particles and micrometeorite impacts, then briefly orbit Mercury in ballistic arcs before falling back to the surface or escaping to space. The composition of this exosphere includes sodium, potassium, calcium, magnesium, and other elements, creating a tenuous atmosphere that's probably been similar throughout Mercury's history because it's continuously regenerated from surface material. When sodium atoms in Mercury's exosphere are illuminated by sunlight, they glow, and telescopes on Earth can detect this sodium emission, seeing Mercury surrounded by a faint glowing cloud, a corona of sodium light that extends beyond the planet's disk. It's a subtle effect but a beautiful one, a reminder that even airless worlds have an interface with space, a zone where solid planet transitions into vacuum through intermediate stages of rarefied gas and individual atomic trajectories. Venus's surface has relatively few impact craters compared to Mercury or the Moon, and the craters that do exist appear relatively fresh, not degraded by billions of years of subsequent impacts. This supports the idea that Venus's surface is geologically young, resurfaced by volcanic activity that buried the ancient cratered terrain. Crater counts suggest that the current surface formed roughly 500 million years ago, which, while ancient by human standards, is young compared to the solar system's 4.5 billion year age. The distribution of craters is also unusual. Venus has no small craters because the thick atmosphere burns up small meteoroids before they reach the surface, acting as a shield against smaller impacts while allowing large objects through. This means Venus's crater record is biased toward large impacts, missing the smaller craters that pepper the Moon and Mercury. Venus's atmosphere and geology work together to constantly renew the surface, removing impact records through volcanic resurfacing, and preventing small impacts from occurring, creating a surface that's simultaneously very old in absolute time but young in terms of preservation age. A paradox that reflects the complex interplay of geological and atmospheric processes. Mars's canyon system, Valles Marineris, might have contained flowing water at some points in the past, with evidence of mineral deposits and sediment layers that suggest episodic flooding. Some scientists hypothesize that Mars might have experienced catastrophic floods, where subsurface water, ice, or underground aquifers suddenly released, carving channels and partially filling the canyon with temporary lakes or seas that eventually froze or evaporated. The idea of a canyon larger than the continental United States occasionally flooding with water creates a dramatic image of Mars's past, a planet where water could suddenly transform landscapes, where dry canyons could become inland seas, where conditions fluctuated between desert and deluge. Even if these floods were temporary, lasting perhaps only years or centuries, they would have created habitable environments where Martian life, if it existed, might have thrived temporarily before the water disappeared again, playing out cycles of habitability that we're only beginning to understand through geological evidence. Jupiter's atmosphere contains colorful clouds arranged in bands parallel to the equator, created by jet streams that alternate direction between zones and belts, with zones being upwelling regions where ammonia ice crystals form white clouds, and belts being downdrafting regions where clouds are thinner and deeper layers show through. The colors come from complex chemistry involving sulfur, phosphorus, and organic compounds created when sunlight breaks apart simpler molecules, though the exact chemistry producing Jupiter's reds, browns, and tans remains somewhat mysterious. The bands are stable features that have persisted for as long as we've been observing Jupiter, though individual storms and features within the bands come and go. The great red spot sits in one of these belts, embedded in the surrounding jet streams like an eddy in a river, fed energy by the wind shear and by Jupiter's internal heat. From space, Jupiter looks like a painted sphere, its cloud tops arranged in beautiful patterns, organic and flowing, more like abstract art than the rigid geometric circles of a typical planet. Titan's atmosphere is about 10 times more massive than Earth's, meaning there's 10 times as much gas per unit area pressing down on Titan's surface, despite the atmosphere only being 1.5 times the pressure, because Titan's gravity is weaker and allows the atmosphere to extend higher and spread out more. This massive atmosphere makes Titan a fascinating place to study atmospheric dynamics because processes that happen slowly or subtly on Earth might be amplified on Titan. The atmosphere also provides excellent insulation, distributing heat and moderating temperature changes, so that despite Titan being so far from the sun and receiving so little sunlight, the temperature doesn't vary dramatically between day and night or between equator and poles. This is similar to Venus's atmospheric heat distribution, but achieved through different mechanisms in a much colder environment. Titan's atmosphere is a major part of what makes the Moon interesting. Without it, Titan would be just another icy satellite, but with it, Titan becomes a world with weather, seasons, wind, clouds, rain, lakes, rivers, and erosion, all the dynamic processes that make planetary surfaces interesting and complex. And so our gentle journey through the planets comes to a close, though the planets themselves will continue their patient orbits long after we've stopped speaking of them, long after you've drifted into sleep. We've traveled from Mercury baking in the sun to Neptune floating in the outer darkness, visiting worlds of fire and ice, wind and silence, surfaces of metal and stone and frozen methane, atmospheres of hydrogen and helium and sulfuric acid. Each planet we explored is unique, carrying its own history, its own collection of moons and rings and storms, its own story written in geology and atmosphere and orbital mechanics. What strikes me most about the planets is their patience. They've been circling the sun for 4.5 billion years, and they'll continue for billions more, unhurried and unconcerned with human time scales. Our worries, our busy days, our anxieties about tomorrow, all of these exist on such brief timescales compared to the slow turning of worlds through space. There's something deeply comforting in that perspective, in remembering that we're part of something vastly larger and older, that the universe has been here long before us and will continue long after, that our individual concerns, however pressing they feel, are held within a cosmic context that makes them manageable, that makes them smaller in the best possible way. You've done wonderfully tonight, staying with me through this exploration or drifting in and out as the words carried you towards sleep. Either way, you've given yourself this time, this space to rest and learn and simply be, without demands or expectations. That's valuable. That's important. In a world that constantly asks for your attention and energy, you've chosen to spend this time on quiet wonder, on learning about distant worlds while your body relaxes and your mind settles. As you fall asleep tonight, maybe you'll dream of Mars's blue sunsets or Titan's methane lakes, of Jupiter's great red spots spinning for centuries or Saturn's impossibly thin rings catching sunlight. Maybe you won't remember any of the specific facts tomorrow, and that's perfectly fine. The purpose wasn't to memorize but to drift, to let your mind wander through the solar system while your body found its way to rest. The planets will still be there tomorrow if you want to learn more, spinning silently in the dark, patient teachers waiting for anyone who takes the time to look up and wonder. Thank you for being here tonight. Thank you for choosing this video, for settling in and letting these words accompany you towards sleep. If you found this helpful, consider subscribing to the Sleepy Science channel for more bedtime explorations of fascinating topics. Give the video a like if you're still awake enough to do so, though I hope you're not. Hope you're already drifting deep into sleep, your breathing slow and even, your mind quiet and at peace. The universe is vast and full of wonders, but right now, the most important universe is the one you're in. Your bed, your room, your body finding its way to rest. Let yourself sink deeper now. Let the planets spin without you for a while. Let the solar system continue its ancient dance while you sleep, held by gravity on a world that's carried humanity since the beginning, floating through space on this beautiful blue planet we call home. Sleep well, rest deeply. And when you wake tomorrow refreshed and renewed, the cosmos will still be here, still full of mysteries and beauty, still waiting patiently for curious minds to explore its wonders. But for now, just rest, just breathe, just sleep. Good night.